So Professor Shrimali is a professor at the Department of Physics, Central University, Rajasthan. He is in fact Dean of Faculty over there, and he's a JNU product. He's got both his MSc and PhD from JNU. He was a postdoctoral fellow with Professor Aihara in the University of Tokyo after that. And he's actually been one of the pioneers of the introduction of chaos and nonlinear science in his area of the world, namely Rajasthan, because he has worked in a number of institutes there. So LNM IIT, then IIT Jodhpur, and now Central University. So he's introduced this subject to a whole new set of people. His specializations, he has research areas include synchronization, multi-stability, chimera states in complex dynamical systems, all of which provide wonderful background for what he's going to speak on today, namely reservoir computing. And he's actually going to speak on reservoir computing with a single driven pendulum, as you can see in his title on the screen. So Manish, over to you.
Yeah, thank you so much, Professor Nilima Gupta. So, first of all, I would like to thank the organizers of this international workshop on reservoir computing and neural network at IIT Madras in online mode, and giving me this opportunity to discuss our recent work, where we have shown that even the single driven pendulum has a remarkable properties of doing the machine learning task as a reservoir in reservoir computing framework. And after the interesting talk of Nitin in chaos helping in the learning, I'll be mostly focusing on the transient dynamics and quasi-periodic region only. So this work was done by my PhD student Swarnendu Mandal at Central University of Rajasthan, and with our collaborator Sudeshna Sinha from IISER Mohali. The work is supported by DST SERB. I will be giving very brief introduction on neural network, reservoir computing, dynamical systems as a reservoir. Then I'll come to the focus of this talk, which is a single node reservoir, the driven pendulum, the scheme dynamics, results and discussion, and also the experimental relation of the idea. And then I will briefly, before concluding, discuss about the comparison of single node with the network reservoir. As we know that this reservoir computing is going to be a very important computational framework, where we use the physical reservoir or the physical system as the part of the network. So if we go back in the neural network framework, we have a traditional this input layer, then set of hidden layers and output, where we give the input and the machine learn the system dynamics, and based on that perform certain complex tasks. And this is basically with the basic understanding of our the brain. We consider the neuron as a working unit of this neural net, which gets the weighted input from the other neurons, and the output is some function of this weighted input with a bias. And this function can be in a very different form, so I'll not go into the details of all this. But if you look at the basic training mechanism in the typical neural net, when we give the input, it goes to the layer by layer, and once the input is encoded in the hidden layer structure, then we have a true target. What we do is predicted the output compare with the true target value, and that is our loss function, and we calculate our loss score, and that is used for the optimization of the weights. We optimize the weights of the network, and then we reset them, and with this recurrence process, we finally try to reduce the loss function and try to get the predicted output which is close to the true target value. And one of the gradient descent method used for the weight optimization is with this algorithm, where the the weight is updated with the previous weight and with the gradient of the function f, which is basically the difference of the predicted value and the target value. And this is the typical the neural net working. Now let's come to the why the reservoir computing is important and how it is different from the traditional neural net. So here what we do is we replace the hidden layer by the physical dynamical system. And since my background is from the dynamical system, I'm mostly interested in what kind of different physical dynamical systems can be used as a reservoir in the reservoir computing framework, where we don't have to really train all the complete network, where we have seen that the optimization of weights is very important. And in the high dimensional system with large number of this hyperparameters, it is computationally difficult task. So if you look at this reservoir computing, which is basically the deep learning framework, and it uses the dynamical system as a computational substrate as a reservoir, and it has a three main component. You give the input to the system with some weights W in, and then there is a reservoir with its own weight W, and then we have a readout, and there we have a output weight required for the getting the desired output. Now in this framework, we don't optimize the input and the reservoir weight, only the output weights are to be optimized. That reduces the computational cost of the system. And this is originally a recurrent neural network architecture based framework, which is suitable for sequentially data processing. And it was derived independently as a equal state network or liquid state machine. So if you look at the relevance of the reservoir computing, so basically we use the physical system or the dynamical system as a reservoir, which has the rich dynamics, which is capable of multiplexing the complex input. So what we are doing is the input is encoded in the high dimensional reservoir, which is basically the dynamical system. And there's a nonlinear memory effects, which is convenient for the sequential task. So these are the basic properties of the reservoir or the dynamical system, which is helping in the computational framework. Now, since we only have to train the output weight in the readout through the linear regression, the relatively it reduces our training cost. And because of this, it is becoming very popular among physicists and non-experts in computer science, and having applications in variety of areas, including medical science and complex systems. So now let's look at the reservoir computing, which can be broadly put into the two categories. One, we can say that we can have an equistate network, or the physical reservoir, which is the real physical system acting as a reservoir. So in the equistate network, what we do is we have the input as a U here, and then there's the reservoir or the equistate network, which is basically the complex network where the nodes are connected with other nodes in the random fashion, and the state of these nodes are xt at a given time t, and then the output is defined as y. Now there can be a connection between the input and the reservoir marked as a blue line here, and the network has the connections which are marked with the red lines. There can also be a feedback and the connection between the reservoir and the output. Now the state of the reservoir x is updated with this rule, where the t plus 1, the next state of the reservoir, is updated with the previous state, and this tan hyperbolic function of the weighted sum of the input and the previous state, and if there's any feedback to the reservoir. once we get the state of the reservoir, which is say X vector, and we have this output weight here. When you multiply with this, you get the output Y. Now, in the training period, what we do is we have a knowledge of Y. So we find out the W out by the linear regression with Y times X inverse. And once we identify the output weight, that can be used to find the later output for any arbitrary given value of X. Another possible the reservoir are the physical reservoirs, where we can consider any physical system as a reservoir. In this talk, with the brief introduction of the eco-state network model system, I will focus on the physical reservoir, which is a single node reservoir. So let's take a very simple example of the eco-state network computing, and let's have the network of 3 nodes only. So we can consider the connection matrix in the 3 node ESN network with this W matrix, and input connection can be given by this vector. And let's take the task of doubling the amplitude of a sine series. Say the input U is given by 0.5 sine 8 pi t, which is some function f. And we would like to double the function, say 2 of f, which is another function g. So this is our task. Now what we do is we consider some, say, 300 training data set, and we compute this function, which is our u function as an input. And then we also have a knowledge about the output, which is g function, which is 2 times f. We also calculate this. Now the state of the reservoir is updated with this function. Now after discarding some initial iterations, say 50 initial iterations, we calculate the state of reservoir. So what we do is we now compute the state of the reservoir S, which is the 3 node network, and the state of these 3 nodes is computed for next 250 steps, and that is recorded. So we have this matrix S. Now we also have an output matrix T, which is calculated from the function G. Now there is a relation between the output matrix T with the W out, which is the weight, and S is your the state of the matrix reservoir state S. Now we can find out this weight W out by this TS inverse, and this can be identified like this. So once we know this, then we can find out the output for any arbitrary the input U, and that is the state of the reservoir S. So this is very simple framework, and you can see that as compared to the traditional neural net where we have to optimize all the weights, here we are only optimizing the W out, which is in the readout matrix. Now with this, I will just give you the few examples of the physical reservoirs which people have considered in the reservoir computing. And these are from different classes, like electronic system. You can have an analog circuit, field programmable gate arrays, VLSI, memristor based systems. In the photonic, you have a optical node arrays, optoelectronic time delay systems, spintronic systems, mechanical systems where you consider the flexible robots. And there's the review article which can be considered to read more about this kind of physical reservoirs. You can also have a biological system acting as the real physical reservoir. So let's now discuss about the dynamical system as a reservoir. And as we know that the dynamical system can be characterized by the set of rules that determines how the points in the state space of the system changes over time. And there can be a set of the governing equations we consider for that. We can consider any example of the dynamical system or network of dynamical system as a reservoir. Some of the examples can be like we can consider the coupled oscillators or delay dynamical systems. And as I mentioned that if we look at the general framework when we start doing the reservoir computing, so it can be put into the three different compartment. One is like encoding the input to the reservoir. So whatever input is given to the system, that is encoded in the state of the reservoir. So that is the part one. Now what we do is once the state of the reservoir is updated with the input, and then it has its own dynamics, governing dynamics, and it evolves with its own rule. And then what we do is we access this reservoir state and then store them. So in time, we store the state of the reservoir. And once the reservoir states are obtained for sufficiently long time, then we optimize the output weight in the readout. And once the output weight is optimized, then our system is now ready for any computational tasks based on the training done. Now, since we are considering the dynamical system as a reservoir, so there are certain criteria required for the reservoir as a candidate. So one is the high dimensionality is required because we have to input the input information in the high dimensional space, and then rich non-linearity is also required, and fading memory is required so that we don't have a long memory effects in the computational framework of the reservoir. Now, we can consider any arbitrary network as a reservoir. As I mentioned, that eco-state network is the example of random network where you can have the nodes connected with other nodes in a completely random fashion. And examples of coupled oscillator reservoirs, there are certain studies in recent past with the phase oscillators, mechanical and chaotic oscillators. Now, my focus in this talk is when we consider the reservoir, which is basically the high dimensional complex network made of the dynamical units. Can we perform the machine learning tasks even by the single node or simple nonlinear system? So since the requirement is in the multiplexing the input in the high dimensional system, and we would like to reduce the dimensionality of the reservoir, so we will be basically using in the temporal domain. So the encoding will be mostly in the temporal domain. So when we look at the literature where the single node or the single neuron these reservoirs were studied, so there are certain studies with the delay feedback systems or chaotic LC or quantum RC nonlinear oscillators, and also there are certain studies on single neuron with time delay feedback. So in all the previous studies, people have considered the time delay, which is effectively making the system high dimensional. So recently we have published about this work in Physical Review E in the month of May, where we have shown that there's a potential of machine learning by the single pendulum. So let's look at the pendulum here, which we would like to be considered as a potential candidate for reservoir. So this is the equation which we are considering, and this is in the absence of external forcing. This is the damped harmonic oscillator, and you can see the time series. There is the damped oscillator function is there, and what we do is we apply the external force, periodic force with this the amplitude f and the frequency omega, and the dynamics of this pendulum in the presence of the external forcing is quasi-periodic. So now what we are going to do is we are basically going to utilize this the transient dynamics and the quasi periodicity for the learning task. So this is the animation where you can see that we are applying the external force, and the system shows the quasi periodic behavior. Now, so before going to utilize the properties of this driven pendulum for the computational task, we would like to first study the dynamical properties of this. So you can see that this the addition of driving force make the dynamics quasi-periodic. And to avoid the resonance, we are not putting the driving force frequency equal to the natural frequency of the system. And the other observation is that the transient dynamic shows the more nonlinearity as compared to the asymptotic behavior, which can be seen in this figure. The top panel shows the bifurcation diagram as a function of the amplitude of the external force in the asymptotic and transient region. In the bottom panel, you have the same bifurcation diagram as a function of the frequency of the external forcing, again in the asymptotic and the transient region. So you can see that the transient region dynamics is more richer and more quasi-periodic as compared to the periodic and motion in the asymptotic state. And what we do is, because we have to encode the input information in the state of the reservoir, we identify the range of the amplitude or the frequency where we are going to encode the information in the pendulum. So in the rest of the talk, I'll be using the range of amplitude between 1 to 2 for encoding the information, and for frequency 0.5 to 1 for encoding the input information. So now when we would like to multiplex the input into the reservoir dynamics, we have 3 choices. Either we can encode the input information in the initial state of the dynamics, or we can encode into the amplitude of the driving force or frequency of the force. So we prefer only the last 2 choices, which are the amplitude and frequency encoding. Since the initial state encoding may not be the good idea, because asymptotically they are reaching to the same attractor, and in that process we are losing the input information. So what we do is we scale the input u in the parameter range where we would like to encode the information. So we have 2 choices. Either we can encode in the amplitudes range from f min to f max, or we can do it in the frequency. So this input data is recorded there, and what we do is, once the information is encoded at the amplitude or the frequency of the driving force, we update the state of the pendulum. So we obtain the state of the reservoir as the states of the x and x dot, which in the state space. And after each input to the reservoir, we reset the state, the initial to 0, 0, so that we are able to again utilize the transient dynamics of the reservoir for next input data set. So now, since we are only utilizing the transient dynamics and where we are storing the input, and it produces the richer nonlinear repository as compared to the asymptotic state, and the reservoir state x is recorded at a fixed sampling rate, kappa omega, and omega is the sampling cycle frequency. So with this x naught to x kappa capital N tau, we get the reservoir state where tau is the sampling interval and is the number of cycles. So for the how long we are considering this, the state of the reservoir. So now for any input point UIT, the reservoir state vector xi is generated from Si for regression. So now what we do is we are going to consider the two different tasks. One is a non-temporal, another is a temporal task, in order to see the performance of the single mode reservoir. So for the non-temporal task, we simply get the state vector x, which is the S reservoir state. And now for the temporal task, because we need the subsequent the event. So what we do is we take the weighted state of this reservoir in the for the previous input up to the some steps m, where m is considered to be some hyperparameter, and this Wj is uniformly distributed between in the range of 0 to 1. So here M acts as a finite memory, and which helps in the basic requirement of the feeding memory requirement of the reservoir. So this is the two ways we are going to update the state of the reservoir and going to use this two vectors for the computational task. So the training scheme is as follows, that for the non-temporal task, we encode the input U to the state of the reservoir, and then we get the vector S, and then we reset again for the next input, and in that process we get the X I as the SI vector for the reservoir, and this is going to be used for the optimization of the weight W out in the readout. Now for the temporal task, we have the input U, and we get the state of the reservoir, and then what we do is for the previous input and so on, we go up to the mth previous input, and there's the weighted sum of this, which is not the sum but the weighted the faded memory, the matrix, which is going to be used for the xi, which is basically state of the reservoir. Now for a complete input signal, the reservoir state vector matrix is formed. So this the matrix is either k kappa n times L dimension, or this is m times kappa n cross L, depending on whether you are considering the non-temporal task or the temporal task. Now we have a relation between the output, which is V is equal to this W, the weight which is going to be optimized, times the state vector of the reservoir R. Now the connection matrix to be calculated with the training data set. So in the training data set, we have the information about the output as well as the reservoir matrix R, and with the more Penrose pseudo inverse, we can the regression, we can find out the W, which is the VR inverse. So it can be a very simple task to work out the weight or the W out in the readout to perform the particular task. So once we calculate the W, then we can find out the output V for any arbitrary input U. So let's look at the non-temporal tasks where we would like to approximate the 7th order polynomial given by this function. So this function is considered as a the non-temporal task approximation. So we do this the encoding both in the amplitude as well as in the frequency. So in order to look at the performance of the reservoir, we have calculated the root mean square error, which is of the order of 10 to the minus 8 to 10 in frequency and amplitude encoding. And you can see that the predicted output is very close to the target value. So yeah. So now, in order to look at the temporal task, we have considered the attractor reconstruction of Lorentz chaotic system. And these are the set of equations for Lorentz system. And we have given the x variable of the system as an input. And we have predicted the y and z variables in the amplitude and frequency encoding. You can see that the predicted values are in close agreement with the target values, with the error of order of minus 10 to the minus 3. So now we have also developed this experimental setup to verify our this numerical results. So we have considered this the experimental setup where we have this two populars and the microcontroller is there, and we have a gyroscope here to transfer the information of the angle of the pendulum, and we can control the forcing amplitude and the frequency of the external force here. So we have done this task of non-temporal fitting of the polynomial where we have done the encoding in the frequency, and we have seen that the predicted output is very close to the target value. We have also checked the performance of this single node reservoir in the presence of noise. We have added the uniformly distributed noise in this range minus 0.01 to 0.01 to the state variable of the system. And again, you can see that the performance of this reservoir in the presence of noise is still is good, and the frequency encoding works a little better as compared to the amplitude encoding, and the temporal task has a less effect of the noise. So these are the few observations there. Now, what we have done, since we wanted to look at the single node reservoir computational abilities, and with this single node reservoir where we have considered the force pendulum, we wanted to extend our study to the more complex behavior of such systems. So one of the example there is a Duffing oscillator. So we have considered the Duffing oscillator, and this bifurcation diagram of Duffing oscillator is shown as a function of the amplitude of this F here. And you can see that there are different regions of periodic, chaotic, and quasi-periodic behavior. We have considered these three different regions, the periodic, chaotic, and quasi-periodic, for our computational task. And in these three regions, we have again used the transient dynamics. So you can see that the transient dynamics behavior is in the lower panel, which is to be utilized for the computing. So here in this table, we have compared the performance of different complexity periodic, quasi-periodic, and chaotic regions, again for the asymptotic and the transient dynamics. So you can see that the performance of the reservoir is better in the transient dynamics as compared to asymptotic dynamics in all the three cases. And also that the quasi-periodic and periodic region shows the better performance as compared to the chaotic region. So, and in fact, the quasi-periodic dynamics is more optimal choice, and the transient dynamics is the better choice as compared to the asymptotic state for the information processing capacities. So we have also checked our results for the network reservoir just to compare our single node reservoir results. Although this cannot be generalized, but just to have one example, we have considered this nodes of 100 oscillators, which are basically chaotic Lorentz oscillators, and they are indirectly connected by the single exponentially decaying system S. So this is the dynamics of this network of Lorentz chaotic oscillators. And when we look at this alpha and epsilon, which are basically the feedback and the coupling strength parameters in the network, what we have done is we have done this parameter space study for the dynamical state of the reservoir. So basically what we have done is we have looked at the collective, the motion or the dynamics of the 100 oscillators, and in this figure we have plotted the amplitude of the average amplitude of the oscillators. So you can see that the system goes from oscillator to steady state as we increase the coupling strength or the feedback alpha, and through this transition boundary, which is marked as a red in the red color. So it is basically system is initially showing the oscillatory behavior and is going to the steady state with the increase of these two parameters. And this transition is not a continuous transition. It is an abrupt discontinuous first order transition. We have also checked the performance of this network reservoir for a certain task, again in the two parameter space, and we have plotted with this color coding the error in the performance. You can see that error is minimum at the boundary when system is going from oscillatory to steady state. And this figure, we show the amplitude of the average amplitude of the network of oscillators and the error as a function of the coupling strength epsilon for a fixed value of alpha. So we fix our value of alpha at certain values, say 3, and then we check the dynamics of the system as well as the computational task performance simultaneously. So you can see that the amplitude of the oscillators goes to 0 at the certain critical coupling strength, and when you go in the reverse direction, it goes back to the oscillatory state at the lower value of epsilon, and there is a hysteresis there, and it is basically a discontinuous first order explosive transition from oscillatory to steady state. Now, when you look at the performance of the reservoir, we have observed that the performance is best near the transition point. So there's a drop in the error, and again there's a rise in the error. So in the forward transition point, you have a best performance of the reservoir where the system is basically in the oscillatory state, but it is at the near the age of transition, and their performance is better as compared to the steady state or the oscillatory state of the system. So now here in this the figure and the table, we have compared the single node and the multi-node network performance for 3 different tasks. The tasks 1 and 2 are the basically reconstruction tasks of Oscillator and Chua system, and task 3 is the filtering of the Mackey glass time series. So you can see that the single node network reservoir, basically the single pendulum, performs equal or even better than the multi-node reservoir in this particular case. But that is not necessarily be true all the time. But the idea is in certain computational tasks, the single node reservoir can also be utilized, and we really don't need the high dimensional network reservoir. So with this, I would like to conclude my talk that we have considered the single force pendulum, which shows the sufficient richness in dynamics to process information for intelligent computation. Instead of multiplexing the input in the state space, so the temporal encoding effectively make it act like a high dimensional system. So which is what we are doing here. We are doing the encoding in the temporal domain, not in the state space, because of our limitation of the single node. The transient dynamics has more information processing capacity as compared to the asymptotic behavior, as we have observed in our study. The input encoding in the quasi-periodic region works better than the periodic and the chaotic region. And at the age of the transition, the performance is better, as we have observed in the network reservoir case. So with this, I thank you, and I'm open for questions.
Yeah, so thank you, Manish.
Yeah.
Questions? See, Manish, I have a question, in fact, which is that you know this old result, right? That things on the edge of chaos are more efficient, right?
Yes.
So here also there is a phase boundary where you actually see better efficiency, which is
Yes.
actually the phase boundary of the oscillatory regime, right?
Yes.
Is there a reason why that should be more efficient?
Because see, what I understand is for this kind of the learning, we need the more stable, as well as at the same time the more complex system.
Okay.
So if you go to the steady state, you are losing the complexity.
Yeah.
And if you are going in the like chaotic region or in the asymptotic state, so again in this case, your although you have a complexity, and but this like basically it is you can say that when we would like to learn from the state of the dynamical state of the system, and if there's no like reverse mapping exactly, so like in the chaotic state, so it is very difficult for the system to learn. So but there are examples, and Nitin was also talking about that chaos and the noise about the learning. But for chaotic system, it may not be very easy to learn because of the non-invertibility, the problems of the system.
Okay. There's a question in the chat box, Rasha Shahnaz. Are you there, Rasha? Hello.
Yeah, so this is about the quasi-periodic region. So I think because again uh, if you look at the periodic, quasi-periodic, and chaotic, so you have a more rich or more dynamics in the quasi-periodic region, but still you are able to map it. So the sensitivity dependence to initial condition is not there. So in some sort, at the same time, you have a more rich dynamics. So that is going to help you in this kind of learning.
Okay.
Sir, can I ask a question?
Yeah, sure.
So generally, when we solve chaotic systems, especially the one that you use in task 1, the numerical solvers have an error of 10 to the power minus 14 as the time goes on because of sensitivity, high sensitivity to initial conditions. In this case, your performance is almost as good as a numerical solver, essentially. Or in some cases, when you said in the previous region, in the last slide where you talked about how in reconstructing the Lorentz system or the Chua circuit, that the single driving the single driving pendulum had performance of 10 to the power minus 14 error. So was that on training data, or like you reconstruct it, or you test it also, like you validate it after that?
Yeah, can you repeat so I can go to the slide also? And,
Yes.
yeah.
So after this, yeah.
This one.
After
Yeah,
this.
this one.
Yeah, this one, yes, sir.
Yeah.
So
Yeah.
here, when you say task 1, sir, it is basically learning what is like fed into, like training the system using the data points.
Yes.
But are we like predicting performance as well in this case? What you've shown here?
Yes. Yeah, this is in the prediction region.
Okay. So because this is almost as good as how numerical solvers are, which is
yes,
seriously good performance. So, I mean,
Yeah.
we can just translate it to, because as time goes on, numerical solvers, the error also increases, but this will take care of that essentially.
Yes.
So we can actually use this for solving for higher time, like chaotic systems for higher time, because this is like really high.
Yeah, you're right. Yeah.
All
Yeah,
right.
thank you. Yeah, this is interesting. So it can be used for that.
So because we have seen like data-driven models these days, and I mean, I'm assuming this is
Yeah.
like the marriage of both, and the performance has really increased exceptionally. So I was wondering if we can do that. So thank you, sir. Thank you.
Yeah. And the length considered is very short, not is around 500 steps or even less than that.
All right, sir. Thank you.
Thank you.
Yeah, so anybody else? So if not, then I think we can thank Professor Manish for a very nice talk. And Manish, I think you will have actually got people to a stage where they can actually start working in this kind of problem. So that's something which is really useful. And
Yes.
yeah, so thanks a lot, and thanks for accepting our invitation. And as I've been telling everybody, we hope to see you all here next year sometime. So let's hope that comes off. So we actually are a little early. So, but I don't want to start early because there'll be people who will be in fact coming in at 6 o'clock. So what we could do is that, is there anything else you would like to tell us? Do you have any?
Yeah. So
Huh?
what we have done recently is also we have used this ESN network to reconstruct the bifurcation diagram.
Okay.
So that is, so we have basically, we start the system in the particular like I don't have that, but I can show it here. Like for example, if I train the reservoir in the periodic region. For example, I consider the amplitude of the forcing F equal to 1. So basically you are in the periodic region, and you are utilizing the transient dynamics. But with this training, if I change the internal parameter of the system and set it to some arbitrary value in this bifurcation diagram, the system is still able to reproduce the dynamics of the system where it was not originally trained. So that is basically you start with the training at the one point, and you change the internal parameter, and you can construct the entire bifurcation diagram almost. So it is in the sufficient long range. So that is the another work which we have recently done. Yeah.
Okay.
And another important problem in the dynamical system, from the dynamical system point of view, because this is one is like for example, the logistic map. If you look at the bifurcation diagram, so you generate by changing the internal parameter of the system, but basically you are training at the particular parameter value or in the particular state of the system, and you construct the entire bifurcation diagram with the learning only in a particular region. Another important the problem in this dynamical system using for the reservoir computing for the dynamical system is that can we like reconstruct the basin, or we can identify the basin of a particular attractor. So if you have a smooth basin, it is possible to do, but in the riddle basin, I have no idea how to do it. So if you train the system for a one particular attractor, and there are more than one attractor in the system, can system predict the other attractor in the system for the different initial conditions or the parameter values?
I see.
Hello. I have a question.
Yeah.
Yeah, I went through your paper on like the model free prediction, in which I forgot the name of the system, like where you like created the bifurcation diagram.
Correct.
I have a question. Like, suppose we have a system like a time delay damped harmonic oscillator. There is like time delay damping, and there is instantaneous amplification. So if we train the reservoir in that regime where the system behaves as a damped harmonic oscillator, can we predict that regime where the system will become an amplified oscillator?
I think it should be possible. I'm not checked, but that is possible. Because we have done for the more complex tasks, so that I don't find as difficult in the kind of the damped harmonic oscillator, and when we change it to the
amplified oscillator.
Yes.
Okay. Thank you for your answer.
Yeah.
Anybody else? If not, then let's thank Professor Manish for a very nice talk.